Molt bon dia a tots. Doncs bé, començarem amb el segon dia empezaremos por el segundo día del Big Data Congress. Hoy, donde como contamos al final del día de ayer, daremos un par de niveles para abajo para explicar algo las tecnologías, un poco más de tripas. Empezamos el día de hoy con un Keynote. Estamos realmente muy contentos de tener a Krishna Gummadi, que es uno de los expertos mundiales reconocido en algorithmic bias. Os leeré un poco su bio, que es realmente impresionante. Él es el responsable de investigación de sistemas en red del Instituto Max Planck, que como sabéis es una de las instituciones de más renombre en el ámbito de la I+D a nivel mundial. Y además es profesor de la Universidad de Saarland. Él terminó su doctorado en 2005 y se licenció en el Bachelor de Technology, Computer Science and Engineering en el 2000 por la Universidad de Washington y el Instituto de Tecnología de Madras, respectivamente. Actualmente sus intereses de investigación están en la medida del análisis, diseño y evaluación de sistemas complejos a la escala de Internet, y sus proyectos actuales se centran en la mejor equidad y transparencia en la toma de decisiones data-driven de los sistemas informáticos de la sociedad. Sus trabajos han recibido diferentes premios internacionales de las mejores conferencias del ACM y EEE, y además es copresidente de numerosas asociaciones y congresos internacionales. Again, we are very happy that you are here and you can enlighten us a bit this morning with your talk. Nos va a hablar sobre discriminación en la toma de decisiones algorítmicas. So the floor is yours.
Thank you. Thank you, Mark. And thanks, everyone, for showing up so early. I'm going to talk about the research that I and others recently started focusing on, which is about foundations of fair algorithmic decision-making. Now, let me start by what I mean by algorithmic decision-making. What I'm referring to is data-driven decision-making, where we use machine learning algorithms to learn how to make decisions using data about past decision outcomes. Now, this sort of learning-based decision-making is increasingly influencing every single aspect of our lives. For instance, if you think of search and recommendation algorithms, they're increasingly determining what information we produce, how we disseminate, and how we consume the information on sites like Facebook, Google, Wikipedia, YouTube, and so on. On these sites, essentially, the recommendation and search algorithms determine what news you see, how your opinions are shaped, and even how you vote and who you meet and what artifacts are available to you at what price. Furthermore, on crowdfunding and gig economy platforms like Uber or Lyft or Kickstarter, you have matchmaking or market-making algorithms that essentially determine which riders are matched to which drivers, which hosts are matched to which travelers, and which venture capitalists are matched to which entrepreneurs. And finally, there are also risk prediction algorithms that are being used to determine where a crime is likely to occur in a city, who is likely to commit it, which children are at the risk of injuring themselves, which employees might be best suited for your company, or which employee might be thinking of leaving your company, as well as who is more likely to be creditworthy and return the loan. Now, given the number of different scenarios that affect our day-to-day lives in a very fundamental way, given the scenarios in which these algorithms are being used, naturally, there are increasingly concerns about the fairness of this decision-making. For instance, there are concerns about the potential for discrimination in predictive analytics algorithms. This is a headline of an article that talks about machine bias, where it says that there is a software that is being used across the country, and the country is the US in this particular case, to predict future criminals, and that it is biased against blacks. Concerns also arise about the opacity or the lack of transparency about the algorithmic decision-making systems. For instance, there are books being written with the titles like Weapons of Math Destruction and the Black Box Society, where people fear that they're being subjected to decisions that they do not fully comprehend, how they're being done, or what data about them is being captured to make those decisions. And finally, there are also concerns about implicit biases in search and recommendation algorithms. For instance, there are concerns that recommender systems are directing people towards news articles or videos of a particular type of opinions more than others. Now, in this talk, I'm going to actually focus on the very first one, which is discrimination. I believe that the afternoon talk might cover more about the transparency and the opacity concerns. Now, I want to emphasize this. Discrimination is a very, very specific type of unfairness, and it doesn't cover all types of unfairness. For instance, if you made decisions completely randomly, it might be non-discriminatory, but it is not, but it would be unfair. Now, discrimination has been pretty well studied in social sciences for over 100 years. It has been studied in political science, moral philosophy, economics, and law as well. In fact, a majority of countries have anti-discrimination laws, and discrimination is even recognized in international human rights laws. But it has not been looked at or studied from a computational perspective. Now, naturally, the first question would be, what is a computational perspective of discrimination, and why is it even needed? So to explain this, what I'm going to do is present to you a real-world case study of a tool that was used to predict recidivism risk. Now, the tool that I'm going to talk about is Compass. It is a tool that is built by a commercial company called Northpoint in the US. Now, what does it mean to predict recidivism risk? Recidivism refers to the likelihood of a criminal reoffending in the future. So what this tool does is it predicts the probability with which somebody might recidivate, that means reoffend in the future. Now, the inputs to the tool, that means the data that it uses to make these predictions, is based on the answers that defendants give. These are criminal defendants give to a long questionnaire. And the outcomes are offered to judges and parole officers in the US. So this is a tool that has been deployed and used in many different jurisdictions in the US. Now, this tool was trained over big data. That means they gathered a lot of data about who has recidivated in the past, the features of all the criminals who reoffended, and then they used that data to train this predictive tool. Now, before they trained it, they took away, that is, they stripped out all the sensitive features like gender or race from the data, because they did not want it to be biased based on gender or race. Now, why did someone think of even designing such a tool? The designers had very lofty goals. They wanted to reform the criminal justice system in the US, which many studies, legal studies, have shown to be biased in terms of the race. So for instance, there are several studies that showed that blacks in the US are often subjected to discriminatory decisions by human judges. So the designers of the tool had an idea, and their idea was that why not nudge or push subjective human decision makers who may be biased with objective algorithmic predictions. Now, the designers thought algorithms have no pre-existing biases, unlike human judges who have biases based on their past experiences. And furthermore, they thought algorithms would always process information in a consistent manner. That means if you gave the same case, that means the same features of a defendant to the algorithm, in the morning or afternoon or in the midnight, it's going to give you the same result, whereas judges are known to make decisions differently before lunch and after lunch. And so they thought, why not train the algorithm to make accurate predictions without the race information in the data? And thereby, you would know that blacks and whites with the same features would get the same outcome. So if a black defendant and a white defendant has exactly the same feature, they would get exactly the same outcome. And this, they thought, would lead to no disparity in treatment. Parity is equality, disparity is inequality, so there would be no inequality in treatment. Two people who have the same features would get the same result. And so it would be non-discriminatory. So this was the idea or the basic argument. So they designed the tool, and everybody thought this was a great idea, and it was actually started being used in multiple different US jurisdictions. Now, 2 years after the tool started being used, an investigative journalism organization called ProPublica wanted to test the claim that this tool is non-discriminatory. So they wanted to check if this is really the case. So what they did was they gathered some data about the predictions the tool made for people in a county called Broward County in Florida. And what I'm showing here are essentially along the rows are the first row is information about people who recidivated, that means who reoffended, and the second row is the people who stayed clean, that means did not reoffend. I'm showing the data separately for black defendants and white defendants within this county of Florida. The columns correspond to the predictions of the tool, so whether the tool predicted somebody to be high risk or low risk. So in the process, what we have is what is traditionally thought of as confusion matrix or truth table, where essentially the green numbers are the people for whom the predictions were correct. So for instance, this 1369 for 1,369 black defendants, they were predicted to be high risk, and they in fact did recidivate. Whereas the numbers in the red are the ones where the tool has predicted wrongly. Okay? So clearly the tool, no tool is going to be perfect. Whenever you're going to make a prediction about the future, you're always going to make mistakes. So the question is, are the mistakes disproportionately affecting blacks compared to whites? So that's the key question that we would like to understand. So to do this, what ProPublica did was they computed what is known as false positive rate. False positive rate is nothing more than the fraction of innocent people, that means who stayed clean, that got the wrong decision. So it is simply computed as 805 divided by 805 plus 990 and 349 divided by 349 plus 1139. Okay? And these were the numbers that they got for blacks and whites. And they also computed what is known as false negative rate. In false negative rate, you compute what fraction of people who are guilty actually got the wrong outcome. That means what fraction of people who are guilty are being let free by the tool. And this is known as a false negative rate, and they computed this one as well. Now, once they did this computation, what they pointed out was the false positive rate for blacks is twice as high as that of whites. And the false negative rate for blacks is half that of whites. Now, false positive rate is actually, having a high false positive rate is actually bad. That means you are innocent, but you're being declared guilty, whereas having lower false negative rate is actually an advantage, because you're guilty, but you're being let go free. So along both dimensions, if you look at these numbers, whites have almost like a factor of 2 advantage compared to the black defendants. And this is what led ProPublica to claim that what is being caused here is something called disparate mistreatment. That means mistreatment is the errors, and there is an inequality in the errors between the two different groups. And this is what led them to publish this article with this headline called Machine Bias, that there is a software used across the country to predict criminals, and it is biased against blacks. Now, the moment they published this article, there was a lot of controversy and confusion. Newspapers reported this as, at best, a case of how algorithms have no ethics, or at worst, how people in power would use algorithms to perpetuate existing social injustices. Now, there was a lot of controversy about this, and in response in certain states, there were, in the US, the use of these algorithmic risk predictions are even banned, or using these tools was declared illegal. Now, the question that that we got interested in, that I would like to ask, is two things. First, why does Compass show such high racial disparity in terms of false positive and false negatives? It was trained without using race information, and the algorithm has no pre-existing biases. So why did it learn? Where did it learn this to be biased? Because in fact, the designers were very well-intentioned. It's not like they tried to perpetuate some things. In fact, they wanted to fix the system, a wrong system, but instead they ended up designing a wrong tool. How? What happened? And the second is it even possible to train the tool to lower the racial disparity? Suppose now that you realize that the tool was doing something wrong, we wanted to fix it, how would we fix it? These are the two questions that we're going to ask. Why did it go wrong? And the second is, how do we fix it? So let's jump into the analysis part of why did the tool learn to make these decisions with high disparity? So to understand this, let's try to understand first how Compass actually learns who is recidivating. Now, it does that by training over data about past outcomes. So typically, in these situations, what you have is you have some data about some defendants. So you have various different features about the defendants. These are features like how many times have they committed crimes in the past, or what is the nature of their crimes, or do they have a stable job? These are the sorts of data that you typically use. So the features refer to whether or not the defendant has a job or has committed crimes in the past and so on. And in addition to that, you also have data about past outcomes. That means this is the big data that they're learning from. That is, who has recidivated and who has stayed clean. Now, the learning challenge is, of course, learning a decision function, which is some statistical function, over the features that would help you separate out the two groups of people, the people who are recidivating and the people who are staying clean. This is the basic thing that you would do in any learning task. So to make this easier to follow, what I'm going to do is I'm representing the same data in a bit more of a pictographical or geometric form, where you have some features along different axes, and each dot corresponds to a defendant. Now, the tick corresponds to defendants who did not recidivate, or who recidivated, and the cross corresponds to people who did not recidivate. Okay? Now, the question is, the goal of Compass is to learn some decision function which ends up being a boundary, decision boundary. That means a sort of a line in the space of the features that would neatly separate out the ticks from the crosses. So in this talk, I'm going to focus on linear boundaries. That means straight lines, because they're a bit easier to talk about. Now, as you can see, you could draw infinite number of straight lines on the plane, but this straight line is doing a pretty good job of separating out the ticks from the crosses, even if you just look at it visually. So the goal of Compass was to learn this sort of a boundary, the one that is most accurate or the least loss in terms of making errors in predictions. Now the question really is, how does Compass actually compute it? How does Compass find this line from the infinite number of lines through this? So what I'm going to do on the next slide is probably the most technical part, but I'll try to explain things at a high level, because it's really important to understand what goes on within in the learning process to understand where the biases actually come from. So how does Compass actually compute these boundaries? So machine learning is a very vast field, but fundamentally, if you think of any learning task, what you do is you actually define a loss function and you optimize for it. Now, different types of learning models use different types of loss functions. That's why you hear a lot of jargon like, neural networks, linear regression, logistic regression, SVM, and all these kinds of things. But fundamentally, what all of them do is they define a function that captures errors or inaccuracy in individual predictions. And what they do is, first, they try to minimize the errors over all examples in the training data. So for instance, here, I'm showing some function. It's the least squared loss function. Forget about the form of the function. The important thing is what you try to do is you sum up the losses across all examples in the training data, and then you try to minimize that loss function. Okay? This is one thing that I would need you to remember. That is, the boundary that you're picking, or the decision boundary that you're picking, is the one that minimizes the loss across all the data points. And the second thing that I would like you to remember is that when you're picking these functions, you have to be able to compute or optimize for them efficiently. And in practice, what people end up doing in learning algorithms is they often end up picking loss functions that are known as convex functions. It's not really important what a convex function is, but these are functions of a certain form that would make it easy to optimize. Because if you started picking arbitrary functions, you're not going to be able to easily optimize. Just remember these two things, that you're summing up the losses over all the training points, and that you cannot take arbitrary loss functions. Now, let's go back to how Compass actually found the most accurate boundary. How did it pick this boundary from all the different infinite number of straight lines that you could draw? The way it did it in this particular case is by minimizing the least squared loss. Okay? Now, let's try to understand how, just from this process, you would learn how does Compass learn to discriminate? It seems like so far everything is going correct. You're trying to learn the boundary that is most accurate. Why would this be discriminatory? To understand this, what I'm going to do next is observe carefully the linear boundary, and what I'm going to reveal to you now are the groups that the points belong to. Okay? So these points actually belong to two different groups. One is the yellow group, and the other is the blue group. Now, these could be genders, or these could be race. Think about them in whatever way you would want. Let's say there is a yellow race and a blue race of points. Now, notice that all of a sudden, this boundary, which was the most accurate boundary for the entire population, is making very few errors for yellow. There is only one yellow dot for which it got a wrong, it made a wrong prediction, whereas it makes lots of errors for blue. And in fact, even the type of errors that it is making are very different. It actually is accepting a person who deserves to be rejected in yellow, and is rejecting a lot of people who deserve to be accepted for blue. So this is what is causing disparate mistreatment or inequality in error rates. So in other words, what is happening is whenever you're learning some decision making, you're always trying to be accurate for the entire population. And when you have different subgroups within the population, if you do not tell the learning algorithm to make sure that it is giving equal error rates for the two different subpopulations, the learning algorithm will simply pick the one that is most optimal for the entire global population, and in the process trade off errors for one, more errors for one, for fewer errors for the other group. In fact, this should not be surprising at all if we actually understood how the learning algorithm was actually working. And that's the point that I wanted to make. Okay? Now notice that you might be tempted to think that, oh, could we not like rotate the line in some way to equalize the error rate? But the moment you start doing that, to equalize the error rates, you will start making more errors for the other group. So there is some trade-off in terms of accuracy and fairness, in terms of like equalizing the error rates between the two different groups. And that's the key point. So to summarize, the cause of error rate disparity is actually simple. If you look at what is the objective of learning, we are training the learning algorithms, in this particular case I'm calling it a classifier, to minimize the sum of individual errors. When you minimize that, it doesn't guarantee that you have average group errors that are equal between the different groups, and that's the main point. Now, of course, you can represent these more formally in terms of like probabilities, but that's the key thing that is going on within the system. Okay? Now that we understood why the error rate disparity arises, let's try to understand how to fix it. Like suppose if you now wanted to train a classifier or a learning, you wanted to learn from data without making this error rate disparity, providing equal error rate, how would you do it? Now this is something that we presented in a paper at the conference. I just put that up as a reference. So how do we learn to avoid discrimination? The idea is actually, at a high level, ridiculously simple. The thing is, you would want to specify the discrimination measures as learning constraints. And then you would want to optimize for accuracy under those constraints. Now, what do I mean by this? So typically, when you try to learn, you try to minimize the overall inaccuracy. And this is the typical problem that you try to solve. Now, if you want fairness, what you start doing is you start adding some additional constraints. These are the constraints that require that the error rates for race B and race, that is blacks and whites, are the same. So now what you're doing is, traditionally in learning, you solve only that, and now you're saying you try to maximize the error, maximize the accuracy and minimize the error as subject to the constraints that the error rates are equal at the level of groups. So essentially, these are what we call as fairness constraints. And what these constraints are doing is they are embedding ethics or values when you're learning. So you're telling the algorithm, here is something that we hold dear. Here is an ethical requirement when you're learning. And you can optimize for accuracy so long as you do not violate that ethical constraint. And those are the things that you're specifying. Now, two important observations. There is no free lunch. Anytime you add an ethical constraint, your overall accuracy of prediction for the entire population is going to decrease. The reason is very simple. Anytime you're optimizing something, when you're trying to solve a problem, the more constraints or the more objectives you lay on it, the less you would be able to optimize for the original goal. So there would be a trade-off in practice between overall accuracy and non-discrimination. And the second interesting thing is, to avoid this thing, to solve this problem, you actually need race information. That means if you really wanted to achieve equal error rates, you shouldn't be removing race information from the training data. So in a strange way, however well-intentioned the original designers of Compass were, they made a mistake by removing race information from the training data. Now, of course, what I mean by using race information is you still have to be careful in the way you use it. You have to use it in the constraints and not in this sort of a function. So this is one of those cases where trying to extrapolate from human decision-making to algorithmic decision-making can have dramatically reverse consequences. So it feels as if like the Compass designers thought like, well, if you were to make humans make decisions in a non-discriminatory manner, by hiding the race information, you would actually be forcing the human judges to make the decisions in a fair manner. But this kind of a logic doesn't always translate to algorithms. You cannot just think of how humans make decisions and think that if you applied the same principles to algorithmic decision-making, they would work. In fact, sometimes it's exactly the opposite of what you would need. So, now, the technical challenge is how do you actually learn efficiently under these constraints? Because typically in learning, you know how to solve this, but you don't know how to solve them with these constraints. Now, the problem is that the above formulations are actually not convex, and you cannot learn them efficiently. That means you need to replace them with some other convex functions. So for instance, typically in the case of learning, you always find some convex surrogates to solve that problem. Now, I'm not going to bore you with the details of how we would actually rewrite it, but essentially what we did, the technical challenge here is how do we rewrite the constraints to make them efficiently learnable. Without going into the details of how we did it, let me just show you some results of once we did the rewriting, and once we solve the learning challenge, do the constraints actually work in practice? So once again, we gathered the recidivism history data set, similar to the one that Compass and others were using. This is the data from Broward County, Florida, and it had the inputs were some features, like arrest charge, number of prior offenses, and the class label was some 2-year recidivism risk prediction. Now, if you trained the traditional learning algorithm, you use your favorite machine learning algorithm, logistic regression or SVM or whatever, when we did that, What we got was an accuracy of prediction of 67%, but in terms of false positive rates, blacks had a 20 percentage points higher false positive rate and 30 percentage points lower false negative rate. And this is bad. This is the traditional classifiers. Then what we did was we trained classifiers with the fairness constraints. That means applying those additional constraints that I talked about. Now, we did get an accuracy of 66%. Now, notice that we did give up a little bit in terms of accuracy. The accuracy is lower. But in terms of the inequality in terms of false positive rate, it fell down from 20 percentage points to 3 percentage points, and false negative rate fell down. The difference between the false negative rates for blacks and whites came down from 30 percentage points to 11 percentage points. In other words, what we ended up doing is decreasing the inequality in the group error rate. We didn't manage to completely fix it to 0, because sometimes this is not possible. But we were able to do that. We were able to minimize it significantly at the cost of some accuracy. Now, one thing is, if you look at these numbers, it feels like in terms of accuracy, you're giving up only 1 percentage point. Now, in this particular data set, we were lucky to be able to find such a boundary, but it's not always the case that, that it would be the same. In certain cases, the accuracy loss could be much higher. So there is no theoretical guarantee that if you try to minimize the group error rates, the loss in accuracy would be this small. Sometimes it can even be higher. OK, so now, before I conclude, let me actually try to step back and point out some high-level takeaway lessons from the Compass story. It's a bit of a tragic story because it was a well-intentioned tool that went horribly wrong because we didn't understand, our people didn't understand how the biases were creeping into the decision-making thing. So what are the takeaways for ethical machine learning? So here is one high-level insight. Many machine learning researchers often don't realize this, but whenever you have a learning objective, they implicitly embody some form of ethics. And the way they end up embodying ethics is they explicitly define the trade-offs in the decision errors. That means if you took a look at the machine learning tasks today, the decision boundary they pick is the one that minimizes the sum of the errors of all their decisions. Now, if you talk to social scientists, they would immediately tell you that that's a very utilitarian way of thinking about decision-making. Now, utilitarian ethics are ones where you say the best decision can be found by looking at how it affects individual people and summing up the utility or the welfare that each person gets from those decisions. Now, that's a very, very utilitarian form of thinking. If you know, if you're familiar with utilitarianism and welfarism literature. But there are lots of scenarios where utilitarian ethics fall short. So for instance, suppose you were making decisions for people within your company. Would you always make decisions in such a way that you say, if I were to make this decision, how much loss would each person suffer, or how much gain would each person suffer? And would you make a decision that is always summing up the losses or summing up the gains? Or would you consider situations where you would say, let me consider the person who is affected the most? That means you would actually minimize the maximum loss that anybody would suffer. Or there are situations when people would consider minimizing the inequality in terms of the utilities or the losses different people would suffer. Now, these are all alternate functions, objective functions. But today, in machine learning, we always try to minimize the sum of losses for all individuals, and we don't consider other types of functions that are very naturally justifiable as well, like minimizing the maximum error for all the people, or minimizing the inequality in the error for all the people. And in fact, what we need to do is to change the learning objectives for other ethical considerations. And in fact, what I talked about today is non-discrimination, which actually requires considering errors not just at the level of individuals, but at the level of groups. And that's what is happening. That's the one high-level insight. Now, when you try to do ethical learning, there are 3 types of challenges that you face. The first is the operationalization challenge. The second is the synthesis, and the third is the analysis. The operationalization challenge is how to formally interpret fairness principles in different algorithmic decision-making scenarios. The synthesis challenge is once you formally interpret, like meaning if you recollect in the talk, at some point I started writing formal statements in terms of equality of errors to guarantee non-discrimination. In that process, I'm formally interpreting the fairness principle. Then the second thing is, how do we design efficient learning mechanisms for the different fairness interpretations? And finally, the analysis is, what are the trade-offs between the different learning objectives? Now, in terms of these three challenges, what computer scientists or machine learning people are pretty good at is doing the synthesis and the analysis challenge, because this is what we do for breakfast, lunch, and dinner. But what is actually very subtle and tricky is the first one, the operationalization challenge, which is an inherently interdisciplinary task, because you have to take some ethical principle and try to put it in formal notation. And to illustrate how tricky it can be, let me point out that so far, we talked about two different operationalizations of discrimination. That means two different formal ways of thinking about this. One is the disparate treatment, which is what Compass guys tried to avoid, and then another thing which I called as disparate mistreatment. So the question is, are we done? Are we done with discrimination? If we just took care of this, is this sufficient to take care of all the different scenarios where algorithmic decision-making scenarios where discrimination can occur? Actually, no. In fact, let me tell you a few more scenarios where you would have to think in a different way about discrimination. The first thing is, I've always assumed so far that the training data is unbiased. That means it is reflecting the ground truth about who is recidivating and who is not recidivating. But what if the training data labels were biased? That means, suppose if these labels were actually generated by humans in the past, then essentially you should worry about bias in the training data. Now, in that case, what is the way in which you would make sure that it is non-discriminatory? There, you would have to look at not error rates, but something called group acceptance rates, which is a different way of formalizing it. Now, I don't have the time to go into the details, but I have references there for the conference papers where you could, that were published by us, where you could look this up. But let me also bring up another point. Could requiring equality in error rates result in all groups being worse off? Now, surprising as this might seem, this can actually happen. That is, if you actually required all groups to have an equal error rate, you might end up with a situation where all groups end up losing. This can happen in specific decision-making scenarios. It didn't happen in the case, in the data set that we talked about, but sometimes actually requiring equality can be bad for all of them. Now, there is a formal way of thinking about this. These are what are known as non-Pareto optimal solutions. And so we can actually talk about a different way of formalizing discrimination that would allow for unequal error rates so long as every group is better off than what they would have gotten if they had demanded parity or equality. And finally, some of you might be wondering, when there are two different groups, why don't we just simply train two different decision boundaries? Why not have one decision boundary for blacks and one decision boundary for whites, so that we can actually do better here? The problem here is the claim of reverse discrimination. Sometimes, when you have two different boundaries for two different groups, it actually causes a lot of tension in the society because one group feels that the other group is actually having it easy. And let's think about what does it mean to have it easy. That means one group feels that more of them would get the positive outcomes if they were judged by the other group's decision boundary, right? Now, actually, there is a catch even here. This is not always the case. So sometimes you can have situations where there are two different boundaries for two different groups, but neither group might want to have the boundary of the other one. So traditionally, there is always this feeling that any time you say that you're going to have two different boundaries for two different groups, people would jump up and say, this is lowering the bar, or this is sort of like an affirmative action, and this is making it easy for the other group. But what we have actually shown is formally there are situations where the data set reveals that the two boundaries can be envy-free. That means no group would want the boundary of the other group. That is what is known as NV freeness. And in those situations, you may be better off picking two different boundaries. So in the end, what we ended up having is not just two different interpretations of discrimination, but 5 different operationalizations or interpretations of discrimination that you might want to use in different contexts. That means it's not like there is one thing that you would pick and use in all different scenarios, but you have to understand the data set correctly before you apply one or more of these. So looking forward from non-discrimination to fair algorithmic decision-making. So far, what I actually talked about is how to learn non-discriminatory classification. But classification, meaning classification is one where you're labeling something as 0 or 1, like recidivating or non-recidivating. But as anyone with background in machine learning knows, that classification is just one of the different types of tasks. In fact, if you're talking about, say, for instance, credit ratings, you're talking about a regression problem. If you're talking about recommendations, you have a set selection problem. When you're talking about search results, you're talking about a ranking problem. When you're talking about matching drivers and riders, you're talking about, that's the matching problem. And finally, if you're talking about unsupervised learning, you have the clustering problem. Now, notice that all that I discussed so far is non-discrimination in the context of classification. And trying to operationalize the principle of non-discrimination in all these different scenarios is actually quite different, and it's quite challenging in its own right. Furthermore, let's take the principle of non-discrimination itself. That is just one of many different fairness or ethical principles that have been studied in social sciences. In fact, for centuries in social sciences, fairness principles have been studied in moral philosophy, law, and communication and media studies. For decades, the fairness principles have been studied in quantitative ways in areas like social welfare theory, social choice theory, and behavioral economics as well. So there is a vast variety of interesting fairness principles that deserve to be applied in various different algorithmic decision-making tasks, and these are all open problems, and this is what I'm investigating, my group is investigating as part of my ERC Advanced grant. So we have scratched the surface in terms of looking at various different things, but this is a very wide open area with many, many open questions that are unanswered. So let me conclude with this slide, summarizing my thoughts about ethics and algorithms. So essentially, there are two separate things one could think about. One is from a societal need. There is a need for defining ethics for algorithms. And from a scientific curiosity perspective, there is a question of looking at ethics through an algorithmic lens. Now, when we talk about ethics for algorithms, whenever you're doing learning algorithms, they will make some errors. But the important thing is not all errors are the same. So for instance, when you're using image annotation algorithms, when the crown that the Queen of England is wearing is identified as shower cap with very high confidence, that's an amusing error. Whereas if the annotation essentially makes, if the image annotation labels people of a particular race as chimpanzees, which actually happened with Google's annotation algorithm, image annotation algorithm, all of a sudden that is no longer amusing. In fact, it is horrifying. And similarly, even with translation, we all know that there are lots of amusing errors that happen when you use Google Translate from one language to the other. But recently, people have shown that there are certain kinds of errors that Google Translate makes that are systematically biased along the lines of gender. So for instance, in Turkish, there is a gender-neutral word, bir, that is actually translated to she when it is jobs like cook, and he when it is a job like engineer. Doctor, this is translated to he, whereas if it is a nurse, it's translated to she. So ethical errors actually make use of algorithms untenable, and the challenge is how to tell the algorithms which of the errors are ethical and unacceptable errors, and which of the errors are actually maybe tolerable. And finally, in terms of scientific curiosity, the challenges here are new interpretations of fairness principles and better understanding of the trade-offs between interpretations, and finally, building learning systems and computing their consequences, which is what we're doing. With that, I'll be happy to take any questions.
So, thank you very much, Krishna. I think so. So first, you did a very good job in order to explain very complex aspects of technology in a very understandable way. I think this is a very hot topic now in research and very important for our society. It's clear that computer scientists cannot work alone in all these fields. Now, we have time for a couple of questions, but I shoot the first one. And then we can bring a micro. Oh, there's a lot of one, but I want to make my one. So this is hot topic in research, which is very important for society. But what are really companies or even public administrations doing? I mean, we all say yes, it's important, but actually there was some researcher had to point out that the tool that was being used was actually biased. You talk and move a lot around the world. What is your sense about private companies and public administration? What are they doing against it?
Yes. I think this is first of all, this is an extremely hot area in the sense of the problems with biases in algorithmic decision-making systems affecting the society directly, right? So we now have adopted some technology that has some consequences that we are only now understanding. Like people have adopted, sometimes you adopt technology before you understand all its negative consequences. And I think that is what makes it very important and very urgent to understand this. The problem here is actually this is one of those few situations when I think we are even missing basic research in terms of understanding how things are going wrong. Meaning, sometimes there are situations where companies end up having some profit motives that might be contradictory to what might be for the general welfare of the public in general. But I think many of the problems here are situations where even the companies would want to fix them, but they often do not know how to fix them. So, for instance, what was the first step that was taken by Google when they realized that their image annotation algorithm went horrendously wrong in labeling certain people as chimpanzees? They didn't know how to fix it because they didn't understand, because while people understand this image annotation using neural networks and those sorts of things, they don't understand how to control for the biases, right? So one of their first reactions was to stop labeling any picture as with the chimpanzee, right? It's not because somebody implicitly wanted it. It's like it's an algorithm that is going haywire, and people didn't know how to control it. And the same thing happened with Compass as well. When ProPublica published their results, the designers of Compass were genuinely surprised. I would like to believe that because they did have a good intent. Yeah, sure. And this is a situation where I think there's a lot of basic things that even machine learning researchers need to do. And I think for a long time, machine learning researchers have often thought of their role as designing accurate systems and everything else, like ethics or fairness, as fluffy, soft stuff, as opposed to they doing the hard stuff. And I think it's time that people recognize that actually when we're doing machine learning, the learning objectives are implicitly embodying the ethics. And I think this is a recognition that researchers have started developing, and they're working towards it. But there is a long, interesting path to be taken.
Sure. And you see, I know, hospitals and such institutions, they have an ethical committee. You know any other type of company which is not related to health that might have or start having ethical responsibilities within their designing teams?
Yes. I think increasingly companies are recognizing, at least the big companies, because they're under scrutiny all the time, right? And in fact, companies like Google, Facebook, even in terms of, they're supporting basic research even to get a handle over these problems because they're not that easy to get a handle over them.
Okay, so let's hand it to, sorry, F2, perdoneu. Okay, so.
Regarding the group-specific boundaries, did you run it? Because I was curious precisely to know if it performed better, and will always perform better a group-specific using group-specific boundaries?
Yes. So it again would depend on the specific data set. So we did look at group-specific boundaries so long as they're NV-free, right? Because if you just picked group-specific boundaries to be most accurate for each group, then you would clearly do better. But then the problem is you would want to also defend yourself against an accusation that it is reverse discrimination. So to avoid reverse discrimination, you actually have to pick two boundaries only when they are envy-free. Now, I can tell you a little bit later precisely what it means, envy-free. Envy-free is this defense that when two boundaries are envy-free, you can say this is not reverse discrimination, even though you're using two boundaries, because no group would benefit by using the other group's boundary. And because there is that constraint of envy-freeness, in addition to just picking two different boundaries, in certain situations, you can actually do better, but you're not guaranteed to do always better. Is that making sense? Because this is the big problem. The charge of reverse discrimination is what prevents people from doing group-specific boundaries. But there is a specific condition under which you could reasonably argue, logically argue, that this is a place where it does make sense for group-specific boundaries and it is not reverse discrimination. And formalizing that is what we did in that case. Now, we did have a data set where it did help, but there are also other data sets where when you don't have that opportunity, you have to pick the same boundary for both groups.
Hi, Erwan Guetel from SEAT. Well, first of all, I would like to thank you for this very interesting presentation, which with the recent enforcement of the GDPR, I'm sure it makes a lot of sense, and that this is one of the aspects that is also trying to be improved at European level, at least. So I had several questions. I hope you can answer them all, but let's see. So the first one
if they are long, you have to pick one.
Yeah. Okay. So I will go for maybe the one on fairness. So eventually, in the Compass example, you said that you managed to decrease the disparity between the two groups. So how would you define a fair enough disparity? And who should decide that this is fair enough?
So that's a great question. So the two separate groups of people who might be, or two different entities who might want to be involved in that. So one is let's talk first from a machine learning or an algorithm from a computer science perspective. What we did was we tried to find, we defined these fairness constraints, and then we tried to find the best that we could do in terms of reducing the disparity. So in the process, we came up with some surrogate functions, and there are other people who are looking at whether if we rewrote the fairness constraints in a different way, whether you could decrease it even further, right? So there is a whole bunch of machine learning researchers who are competing on the technical things of like how would you define the proper surrogate or the proxy functions that would achieve the best possible thing. That is one. Then there is a separate thing of what is the right thing to do here, right? Like that would essentially be determined by the domain experts. So for instance, we tried to simultaneously minimize false positive rate and false negative rate. Whereas somebody might say, in this particular situation, because this is a legal domain, what we care about is false positives and not false negatives. Because false positives are like innocent people being punished, whereas false negatives is guilty people being let go. So in a specific decision-making scenario, if it is in legal domain, you might want to emphasize false positive rate, in which case you would say, leave out the false negative rate. So, but those are decisions that have to be made by domain experts. And this is where both of them need to work together in terms of domain experts defining what the objectives are, and the machine learning researchers actually translating them into the precise constraints and pointing out that if you wanted to have equal false positive and false negative rate, it's going to be more tougher than just having equal false positive rate and so on. So this is the interdisciplinary dialogue that unfortunately doesn't happen often because social scientists and computer scientists seem to be living in, still need to find the right language to talk to each other and appreciate how to communicate, because formal interpretation of a fairness principle is always the tricky challenge.
Okay, so now the last 20 seconds question and 30 seconds answer.
Okay, very interesting question. But I wanted to post a reflection about that perhaps the worst bias is the bias that we commit expressing the ethical issue. Okay? Because if you do this exercise with several blocks, for example, men and women, cis and trans people, people from one or another religion, in fact, any feature is a discriminatory variable. Perhaps the accuracy is going down, 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 and down. And I know that in the USA, the people is very worried with identity politics. And perhaps the problem is that the black people is more worried about the accuracy in the group, not the black people, in the group of the criminal black people, than he is worried about the accuracy of the overall algorithm.
Mm-hmm.
What do you think about this?
So I just want, because I have to be short,
yes.
Let me point out that actually I worry a bit about the use of the word accuracy, because accuracy makes people feel like, the word makes you feel like, of course, why wouldn't you go for something that is accurate? And I also dislike this thing of notion of trade-off between accuracy and fairness. But instead, I would encourage people to actually look at what is the accuracy thing actually representing. It is representing a social choice of trying to minimize the sum of errors for all people, as opposed to something else, like minimizing the maximum error or minimizing the inequality of the errors, right? So you can make it, and these are social choices that are often hidden behind these words like accuracy and fairness, and all of a sudden, somehow, if you care about fairness, you're not being accurate. And I think that's a very, very misleading, unfortunate usage of terms that we are stuck with today, but it's worth understanding that at a deeper level as to the choices that we're making.
Okay, so thanks a lot. Let's applaud the speaker again for such an enlightening talk, and as you see, it has worth a lot of interest. So, ho deixem aquí amb la propera sessió d'Effective Technology Stacks que liderarà el Daniel González.